P block elements. Well, we've seen halogens, we've seen group 7. So let's begin with group 6 today. Group 6A, popularly called oxygen family. Oxygen being the most popular member of the family. Oxygen, sulfur, selenium, tellurium, polonium. The configuration is going to be NS2NP4. The electronic configuration will be NS2NP4. And again, very popularly, this family is given this name chalcogens. Who will tell me why chalcogens? Oxygen family called chalcogens. Why? Anyone? See, literally it means ore forming elements. The term chalcogen means ore forming elements. So those of you who would have seen the basic class on metallurgy would admit that so many oxides and sulfides are minerals. The term chalcogen literally means ore forming elements, and so many minerals are oxides or sulfides, even selenides. So because they were invariably there in so many ores, this name was given to the family chalcogens, ore forming elements, of which this is the only gaseous element. The rest are solid. Polonium is going to be radioactive. The oxygen is gaseous, rest are solids, because oxygen is going to exist as a discrete diatomic molecule. Oxygen is going to be a diatomic molecule or double bond O, and the rest have been found to be octatomic. The rest are octatomic. So oxygen exists as a discrete diatomic molecule. The rest of them will be octatomic. Oxygen diatomic, rest octatomic. So the rest have higher molecular mass, and expectedly they are solids. Expectedly they are solids. Again, this tendency to form 8-membered rings, will look into the structure of these octatomic rings. This tendency to form 8-membered rings, 8-membered puckered rings they are called, is found to be maximum in sulfur and decreases down the group. So repeat, oxygen is diatomic, the rest are octatomic, and the tendency to form 8-membered staggered or puckered rings is found to be maximum for sulfur. This is the way it's going to exist in form of 8-membered puckered ring, where every sulfur atom is found to be sp2 hybridized, 2 bond pair, 2 lone pair, and the atomicity is 8. Atomicity is 8. Even in vapor form, the formula will be S8. The formula will be S8. Oxygen is diatomic, the rest are octatomic, higher molecular weight, expected to be solids. I repeat, the tendency to form 8-membered rings is found to be maximum in sulfur, decreases down the group. And who will want to explain me why oxygen is diatomic and the sulfur is octatomic? Anyone? No? Anyone? Oxygen is diatomic and the rest are octatomic. Sulfur is octatomic because the answer lies in the bond energy values. It's found that O double bond O, the bond energy of O double bond O is much greater than twice O single bond O. O double bond O bond energy is found to be almost thrice, 3 times O single bond O bond energy. Alright. Whereas for sulfur, this S double bond S bond energy is found to be considerably smaller than twice sulfur bond. So repeat, the answer lies in the values of bond energy. S double bond S will have much less bond energy than twice sulfur single bond energy. And this is where oxygen is happy forming a double bond than two single bonds. Oxygen is happy forming a double bond than two single bonds. Sulfur on the contrary, and even the rest of them, given an opportunity, would want to form two single bonds than a double bond. Bond energy, recall, is the amount of energy released when the bond is formed. So sulfur would prefer to form two single bonds. Sulfur would prefer to form two single bonds instead of a double bond. Oxygen is a double bonded covalent diatomic molecule, and sulfur is going to exist in 8-membered rings. Alright, now this tendency to form two single bonds instead of double bond would lead to a ring formation, Fair enough? And let's very quickly go into the general periodic properties and periodic trends of this family: oxygen, sulfur, selenium, tellurium, polonium. Certainly, down the graph, radii, volume, density, melting point, boiling point are bound to increase. All right. And because we're talking of group 6, which is a p block element, next to halogens, when it comes to the right hand side of the periodic table, they're supposed to be naturally electronegative. So the emphasis, the focus would be upon their electronegative nature, the tendency to gain electrons, and certainly it decreases down the graph. So this would be the order of ionization energy, electronegativity, electron affinity, now higher electronegativity, more electron affinity, tendency to gain electrons would reflect acidic behavior. Fine, non-metallic behavior. And down the graph, as ionization energy decreases, it's more readily available to donate electrons. This might well be taken as the order of metallic character. Although, you know, with this family, like halogens, we associate electronegative, acidic behavior, non-metallic behavior, but down the graph, as ionization energy decreases, they are prepared to lose electron, and you will find that tellurium is going to behave fairly metallic. All right. Now talking about, say, their oxidation states, like other groups, you know, the minimum oxidation number would be group number -8, which is -2. The maximum oxidation number would be the group number, which is +6. So the oxidation number will be between -2 to +6. Again, you realize +6 will not be possible for oxygen due to absence of d orbitals. Oxygen is the second most electronegative element, will want to stay in a negative oxidation state. Other than fluorides, you know, oxygen is -2 or -1. It's -1 in peroxides, you know, about superoxides. So other than fluorides, oxygen is negative. But by and large, the permissible oxidation states are -2 to +6. Talking about oxidation state, what comes to mind is, you know, the lower elements of p block. Another phenomena which we have learned before is inert pair effect. Where although it's more prominent in nitrogen family and carbon family, the trend begins in oxygen family, you know, talking about the right hand side of the periodic table. I repeat, although the phenomena will be more prominent in nitrogen family and carbon family, we have done it before in class 11 bonding, if you remember, and we are attributing factors like screening effect, presence of d and f orbitals towards inert pair effect, and eventually lanthanide contraction also. And eventually we had realized that, you know, for suppose selenium, tellurium, sulfur, selenium, tellurium, where +6 is supposed to be the natural oxidation state, because that's supposed to give it the inert gas configuration, and it's also found to have an oxidation state lower than the normal oxidation state by 2 units. It's because of the inertness of the H2 electrons, you know that. And by the end of the discussion, you know, we had concluded that the easiest way to remember it, moving down, the lower state will become more stable. Moving down, the lower state will become more stable. Now this was for oxygen family. You know, for nitrogen family, arsenic, antimony, bismuth, the corresponding oxidation states might well be +5 and +3, where, let's not forget, the higher oxidation state will always be the natural oxidation state. The higher oxidation state will be the natural oxidation state. Lowering by the natural oxidation state by 2 units would be explained by inert pair effect. And different problems based on these ideas would require this conclusion that, you know, moving down, the lower state will become more stable. Moving down, the lower state will become more stable. So if they ask you to compare the stability of the higher and the lower state, I mean, this will be the order of stability of the higher oxidation state, this will be the order of stability of the lower oxidation state. Same for nitrogen family, and as I repeat, in nitrogen family and carbon family, the effects will be more prominent. In nitrogen and carbon family, the effects will be more prominent. Guess I have told you, for bismuth, +3 is so very prominent that Bi +5 doesn't exist other than BiF5. BiF5 is supposed to be the only molecule where bismuth is +5. Only fluorine has the audacity to make it +5, again because fluorine is most electronegative. But other than the fluoride, bismuth is never found in +5 state. The inert pair effect is so prominent, it's found in +3 state only. Alright. And at the end of everything I've told you, moving down, the lower states will be more stable. A few tricks learned in D block also. Let's move on from say the physical and periodic trends to the chemical behavior. We'll begin with hydrides. Hydrides of group 6. Hydrides of group 6 will be this look, MH2, because they're supposed to be divalent. Expected to be the negative end of the molecule. H2O, H2S, H2SE, H2TE being the hydrides of group 6. Yes or no? So water, you know, is going to be a liquid and the rest are going to be gaseous. Let me also tell you, colorless, poisonous gases at room temperature. Alright. And right away, tell me if this should be the order of the following or not. We'll begin with thermal stability. Covalent character. Remember, for covalent character, you would have wanted the central element to be smaller, more electronegative. Yes or no? And H2O, bond angle. Certainly, bond angle. Now, when I mean thermal stability, I've kind of expressed bond energy, and the reverse has to be the order of. The reverse has to be the order of bond length. Bond length. More the bond length, easier it's to break. And with hydrides, we'll always associate some kind of acidity. You know, although the acidity was very prominent in group 7, the hydracids of group 7 were the strongest acids. HCl, HBr, HI. They're not very acidic, but this has to be the order of acidity. You know, in hydracids, we're always bothered about the size of the element and the bond length. and things which I tell you again towards the end of chemical bonding, where this bond angle is around 105 degrees. This is almost 105 degrees, and because it continuously drops down, it keeps on decreasing, and maybe by the time you reach H2SE or H2TE, the bond angle is around 90 degrees. Recall I had said all of it in class 11 bonding, that it starts with 105 degrees. To explain this, we are using hybridization and VACPR, and down the graph, because the bond angle is decreasing, and eventually it is close to 90 degrees, which will not require any fancy ideas, but overlap of pure p orbitals, I hope you are getting me. The rule is, in bonding, all the phenomena we learn one by one. In group 2, boron hydrides and chlorides, beryllium hydrides and chlorides, I'm sorry, we came to know about the 3 electron 2 center bond, 2 electron 3 center bond, banana bonding, but all of them are theories, all of them are ideas, they're phenomena, and it's about requirement. For water to explain 105, we need to go through hybridization and talk of the non-equivalency of bond pair and lone pair to bring it down from 109 to 105. But H2TE and this NP4, NP4 is going to be a situation of this kind. It's going to be 2 p orbitals having single electrons overlapping with hydrogen. And if I don't go into any complications, if I don't buy any theory, overlap of p orbitals only, px, py, pz, or any p orbitals being mutually perpendicular, overlap of pure p orbitals is going to explain 90 degree bond angle. And a very recent type of questions which is featuring in different exams is they started asking percentage hybrid nature, percentage pure nature. I have told you, for a given compound, if the bond angle is more towards the expected bond angle, in hybridization more will be the hybridized nature of the bond. If the bond angle is more towards pure p orbital overlap, not requiring hybridization, we say more p character, of the bond. So moving down as the bond angle is decreasing, I might very well say that these bonds, we've talked about bond length and all, this also is the order of p character in these bonds, and this might be taken as the order of hybridized nature of these bonds. Fair enough? I repeat, the rule is, for a compound, if the bond angle is more towards the expected bond angle, using hybridization you say more hybridized character of the bonds. And if it's more about pure p overlap, you say more p character in those bonds. So this might well be the order of p character, this might well be the order of hybridized character. What is a liquid? Because of hydrogen bonding, you can keep it in a different league altogether, hydrogen bonding, and for the rest of them there is no hydrogen bonding. So what is the force working here? Van der Waals force. And for Van der Waals force, which is proportional to molecular weight, the order would be H2T more than H2SE more than H2S. So this might be a little dicey at times. The order of boiling point is going to be H2O more than, and then you'll find H2TE more than H2SE more than H2S. Should not be very surprising, because I've kept water in a different league, I told you, because of hydrogen bonding, and for the rest of them I'm considering Van der Waals force which is proportional to molecular weight. So the second member, the second hydride of the family, which is H2S in this family, happens to be the one which is most volatile. We saw the same for HCl, we saw the same for hydrochloric acid. Yes or no? Yes or no? And we are expecting the same for ammonia, phosphine, arsine, stilbene, and bismuthine. The order of boiling point would be ammonia maximum because of hydrogen bonding, and then BiH3 more than stilbene more than, arsine more than, phosphine like H2S, pH3 would be most volatile. I repeat, the second hydride of the family, due to absence of hydrogen bonding and minimum van der Waals force, would eventually be the one with maximum volatility, minimum boiling point. I hope it's clear to all of you. Order of boiling point. Fine. These hydrides, where we have talked about, bond angle, the stability, acidic nature and all, they all burn with a blue flame, producing dioxides. Please carry on. Group 6 hydrides burn in air with a blue flame, obviously other than water. Water will not burn. Other than water, the rest would burn with a blue flame, producing dioxides, Other than water, group 6 hydrides would burn with a blue flame, producing dioxides. And I guess I told you before, for group 6, you'll have two kind of oxides, dioxides and trioxides. We have grown watching learning sulfur dioxide as sulfurous anhydride, sulfur trioxide as sulfuric anhydride. So we are aware about two oxides of group 6. But out of these two oxides, I might have said before, dioxide is the natural oxide. We also end up learning that sulfur dioxide to sulfur trioxide in contact process requires a catalyst. Yes or no? So even if they give you sulfur plus excess oxygen, sulfur with excess oxygen, you are expected to write sulfur dioxide and not sulfur trioxide. And minutes ago I told you group 6 hydride, if burned, would produce dioxides. Although group 6 is going to have dioxide and trioxide, very quickly SO2, SCO2, TeO2, and we also know about the corresponding trioxides. It's supposed to be acidic oxides? Yes or no? Metallic oxides is supposed to be basic. They're supposed to be acidic oxides, electronegative oxides. All right. And then only sulfur dioxide is gaseous, the rest are solid. And speaking more about the dioxide, because they are the more stable and the natural oxides, this is the only one which is gaseous, the rest are solids. This certainly is going to be the order of acidity. I repeat, non-metallic oxides in what are supposed to give you the oxyacids. For hydracids we bother about the bond length. For oxyacids, I am kind of repeating it so many times. Again, it's worth it, because you will want to keep in mind, for hydracids it's about bond length. Bond length zyada hoga, easy to break, it's going to be more acidic, and down the graph the acidity would be higher. For oxyacids or oxides, the treatment for oxides and oxyacids should be exactly the same, because these oxides in water would form the oxyacids. Yes or no? We are not bothered about the size of the element. It's about electronegativity. In oxyacids, anyone with any kind of doubt over it? And down the graph, because electronegativity would decrease, acidity of the oxide or oxyacid would decrease. Fine. And then we are also aware about the kind of acids which they produce. Sulfur dioxide, for instance, would go into water forming H2SO3. That's why it's called sulfurous anhydride. SO3 would go in water forming H2SO4. It's called sulfuric anhydride. Simple to recall, not only for these two but for all of them, because I've told you in hydrolysis, let me not call it hydrolysis, it's hydration. At my end at times, goof it up. I call it hydrolysis when it should be calling hydration, but you know the difference. Hydrolysis will be where water is cleaving bonds, is breaking, ripping molecules apart, bonds apart. This is hydration, and in hydration oxidation number will be constant. So this will give you the +4 val acid, this will give you the +6 val acid. Sulfurous anhydride, sulfuric anhydride, us acid, ic acid, sulfurous sulfuric मालूम है, selenous selenic, tellurous telluric are also expected names. Fine. If this is the order of acidity, and this also happens to be the order of solubility in water, you will find TeO2 to start behaving fairly amphoteric. TeO2 will start behaving amphoteric. The way beryllium oxide in group 2 was behaving amphoteric, because they are down the group, the basic nature was increasing, and BeO2, beryllium oxide BeO, was interacting with acids also, was interacting with bases also. I'm sorry. So TeO2 would start behaving amphoteric. Down the group acidity decreases despite an electronegative oxide. It will start behaving like a basic oxide, dissolve both in acid and a base. Now it's dissolving in base is not surprising, because they're supposed to be electronegative oxides, they're supposed to be acidic, but it would react with HCl also, react with nitric acid also. So these statements should be kept in mind. Tellurium oxide would start behaving amphoteric, would react with an acid as well as an alkali. When it comes to dissolving in an acid or alkali, I have told you it's about forming a salt only, which is soluble. We move on, and we will want to spend a little more time upon the oxyacids of this particular family. Oxides of oxyacids of group 6, hydrides of group 5 are going to be more significant. I told you they are going to form two classes of oxyacids, H2SO3 and H2SO4, H2SeO3 and H2SeO4, H2TeO3 and H2TeO4, sulfurous, selenous, tellurous. Sulfurous, selenous and tellurous. Similarly, sulfuric, selenic, and telluric, as expected. The lower oxidation state will oxide or oxyacid is called the us acid, and this is going to be the ic acid. This certainly has to be the order of acidity. You realize, because we don't bother about the size and bond length, we are bothered about the electronegativity. So this has to be the order of acidity. Down the group, electronegativity will decrease and the acidity would fall down. And while comparing the lower and the higher oxidation state of the same element, who will tell me which is more acidic? Higher oxidation state. Because I've again kind of repeated it so many times, between ferrous and ferric, ferric is more electronegative. So moving down, comparing the lower and the higher oxidation state wala acid of an element, moving down you will find acidity increasing. All right. Halides. Group 6 is going to form two kind of halides, hexahalides and tetrahalides. I guess I can rub this. Hexahalides and tetrahalides. Talking about the hexahalides,